welcome back. I see some new faces in here as well. How many are new that weren't here this morning? Almost half. And those that are new here, have you used Unity before?
Yes.
Some of you? All right. Well, we're going to be talking kind of about higher level concepts in Unity. So if you know Unity, that's great. That's helpful. But also, if you haven't used Unity before, some of these concepts will apply to things outside of Unity as well. We're going to start talking a little bit about latency and specifically to Unity, some tricks to reduce that latency and some trade-offs of latency. As I'm sure all of you are very aware, latency is a very important issue for virtual reality. If there's lots of latency in the system, users are more likely to get sick. It's one of the primary contributors to simulator sickness. Although companies like Oculus are starting to do very well on that and getting the latency extremely low, and latency is becoming less and less of an issue. That's sort of one of the engineering challenges of virtual reality is getting the latency down. Those are starting to become solved. The more challenging issues of virtual reality are things like human physiology. That's a little bit harder to change. As far as if your different senses don't match up, then that can cause simulators. So we can talk about that. But first I want to mention there's something called vertical sync in essentially any type of display hardware. What happens is that the rendering engine renders the scene, and then it needs to start rendering the scene again. And so it also works with the display that it needs to display that scene on the screen. And it needs to, how it works in a typical display using today's technology is it uses a raster pattern, at least most displays, that scan out the top leftmost pixel first, and then it moves to the right, and it scans out an entire frame over a period of about 16, 17 milliseconds of time. So the bottom part of the screen is more delayed than the top part of the screen. And that's some interesting results occur because as you rotate the head, the top will be more correct than the bottom, and it will kind of add a little bit of shearing to the scene as you rotate the head. One way to get past that is to not wait until that entire scene is ready to be updated on the display, but instead render as fast as you can. So you might only render, say, 20 scan lines, and then maybe you're ready with a new image. You can say, okay, now for the next 20 scan lines, I can render again and be very updated, provide the latest rendering essentially. So when you get the last part of the screen, it might render this part with the latest information. And that results in faster head-mounted display systems, less simulator signals. However, there's a trade-off for that. You'll see some what we call visual tearing because there's this sudden discontinuity between those rendered frames, and you'll see this subset of the image offset from the following scan lines. And that's called tearing. Some people have reported that is very bad for them, that it's a problem. They feel like it can cause simulator sickness. Myself, it doesn't bug me at all. So it's sort of a personal preference. Myself, I'm a latency guy. That's what I did my dissertation on. So I'm very biased towards reducing latency. I don't care if it tears. But other people like Oculus have different opinions that they think, wow, the tearing is worse than latency. So it kind of depends on you as an individual. Virtual reality is not something that's consistent across individuals. Different people get sick in different ways. So there's some obvious things we can do to reduce simulator sickness, which we can talk about today. But really, you need to create your applications so that they're configurable for user preferences. Okay, with that, I'm going to show a quick example of a way to configure code that is not done with the Oculus Unity code base. And so let me go ahead and show that. So that's the Unity screen for those of you who haven't seen Unity before. This is the editor so we can modify the scripts. Now I'm just going to take mine to see if I can find this line of code. This drove me crazy for the longest time. This line of code right here in OVR camera controller, which we talked briefly about this script earlier this morning. There was the OVR player controller, which controls navigation and such in the scene. The OVR camera controller controls the Unity cameras for the left and right. Now, it's interesting in Unity, when you wait on that vertical sync, which what I was talking about, if you turn vertical sync off, it only renders a subset of the scene as fast as it can, versus vertical sync locks it to the refresh rate of the scene at 60 hertz. And so the bottom part of the screen will be slower than the top. However, in Unity, as far as I can tell, it's adding about 2 to 3 frames of delay. It's not just one added frame of delay, it's adding an extra buffer, an extra frame to the scene. So in Unity, there's more latency when you have this vertical sync on that is waiting until the entire screen updates. Don't update the screen until the full render has been complete. Locked to that 60 hertz. That was pretty frustrating to me because I don't like latency. So what I found, and I tried to force that off, you can change that in your video card settings. So if you go to NVIDIA control settings, you can say, don't wait on vertical sync, turn that off. But in some cases, it was still very latent using Unity. So it was driving me crazy. Why is that the case? It turns out it's this line of code right here. When in Unity, Oculus set this code, when you have your maximum setting to the best settings possible, Unity has some settings that you can set, as fast as you can or the highest quality. When you set it to the highest quality, right there, when that value is set, then it sets VSync on all the time. Even if you want to turn it off, or you turn it off in your control settings, or there's a place within Unity that you can say preferences, don't wait on vertical sync. So you can turn it on in those two places, but it will still be on because of this line of code. So I wanted that to be configurable to have the option to turn it on or off. So that's a very important line when it comes to latency. And I'd also like to mention Oculus has something called a latency meter that actually Zach here has brought one, and he'd like to share what he's found in his experiences of playing with that.
So I think you probably just answered my reason for bringing this, but I'll show everybody how it works really quick. It's really fast. It's a very simple concept. So you replace one of your lenses with this little blob of plastic, and there's a USB cable that is output from this device. There's a small CPU in there, and it's trying to measure round trip, what they call motion to photon. So when you hit the button on the front, let me fire up. Unity scene here. So I'm just running into normal Tuscany demo. You can't see it. When I push this little button, it'll start blinking, and it's sending a command out the cable down through your renderer. And Unity actually intercepts and starts blinking black and white squares directly under this. There's a photosensor that measures and averages a bunch of samples and gives you this nice little number, 23 milliseconds. Now, the reason I brought it today is I wanted to ask all kinds of people about this crazy thing I was seeing when I run the Unity version of that same scene, that same house. I'll show you what happens. So here is the pre-built Unity scene. The house, you only have one choice, Riftastic, maximum visual quality. And I'll fire it up. It's pretty much the same content. I see similar frame rates if I run fraps to measure frame rates. But when I hit the latency tester, maybe you can't see this, it goes from 20 to 30 milliseconds to 100 plus, about 3 times as much, as stated. Overriding this in the NVIDIA control panel doesn't work. Apparently that is a very, very, very important fix to know about. I can't believe they did that. That's going in the forums. Yeah, so it's just that simple. You just replace your lens, do some tests, put your lens back in and go back to work. One pro tip, try to do that inside a big Ziploc bag. Dust gets in there, just bothers you like crazy. And while I'm standing up here, I'm just real curious how many people are local. Minnesota? Small number, okay. Even if you're not local, I organize the local VR group and VR and human-computer interface and the local international game developers. We just coincidentally scheduled a social for 4 p.m. on Wednesday, a block and a half north of here at Buffalo Wild Wings. So if you're staying along after the conference, a little bit later, stop up there. It's just a bar. We're going to have shared screen multiplayer games. Tower Fall. There's a great one called Gang Beasts. All these great games where you drink and you shout at the screen and you shout at each other and a little bit of shoving. And all you kids with your internets are totally missing out. You gotta be there in the room so you can actually shout at the person next to you. So I'll put a little stack of cards up here. You can just grab one, go on our Eventbrite and find the address and everything. But thanks.
Exactly. That's a great point for those of you that are not local. These to form different groups in different cities. I don't have one in my city yet. In North Carolina, is anyone here from North Carolina? All right, there we go. Maybe we need to start one of those groups as well. Okay, so I'll go ahead and get back to the slides. This next I guess 20 minutes or so will be more high-level concepts that some of these is implemented in Unity, but it also apply to any application, whether that's in Unity. So the first point I'd like to make is
I should say one more thing.
Sure.
Don't buy one of these. It's integrated in the dev kit too.
Right, the dev kit being shipped. In fact, you can't buy that dev kit, the former dev kit anymore. That's been discontinued, so you have to wait until July for the new dev kit.
If you want to apply this concept to other displays, they've open sourced all the hardware and firmware. And I would think in theory you can just tape it, more or less tape it to any screen and measure the latency. Prior to this, I would do things with high-speed cameras and then analyze frame by frame, real-world ping pong ball versus display ping pong ball for Connect, let's say. It's awful. You don't want to do that. Pushing a button, getting a number, that's the way to do it.
Okay. Here, earlier I showed, this is kind of just a very basic concept, but sometimes these basic concepts, like after you see it, you think, wow, that's sort of obvious. Right? But in this case, I didn't think about it until I thought, oh, maybe I'll try that. And then once I tried it, I was like, wow, that makes such a difference. So in the standard 6 Sense Entertainment, for those of you that don't know, that is 6 Sense Entertainment does tracking specifically for gaming, and they have something called the Razer Hydra controller, actually built by a different company that licensed their technology, and I have no idea where that went. These are handheld controllers, so you have position and orientation. They're electromagnetic trackers, but they also have these lots of options for buttons and analog sticks and such. The new system is coming out in around July, August time frame, where these are wireless and you can have up to 5 track points. So you can track the head, you can track the whole torso. You may not need to track the head if you're using the Oculus Rift with the position tracking company. But Danny from 6 Sense, who unfortunately wasn't able to be here today, he's tracked the feet and some really cool avatars by tracking more than using 2 tracking points. You can do a lot more on this. And the new system will also be have more precision. There won't be quite as much distortion as there is in the Razer Hydra. So as you can see here, this is the interface in the hand. So in the previous demo, when you wanted to see what are the mappings of the control, it would just come up in your field of view, always in front of you, which gets in the way, and maybe you don't want it there. Here, I simply tore that image, they have it in half, modified the image because my interface is a little bit different as far as what buttons do what. And I put an image, that's all this is a transparent texture map attached as a child of the hand. And then you push one of those buttons, which is probably listed somewhere on here. One of these buttons, I think it's probably this button, it's not listed, is that it turns this off and on. So it's not always annoying if you already know what buttons do what. But the point is, if you're just beginning and you don't know this interface, think of an Xbox controller. How nice would it be if, for console games, if you just look back and say, oh, that's the, maybe the fire button's obvious, but some other functionality. You simply look at your hands and you know what button does what. And because you can't see this physically, the real world controller, it's nice to have this representation here. And so your fingers aren't necessarily labeled, but you can kind of feel where those buttons are and know, oh, this is what I want to do, and just push that button. So it makes it much easier. And ideally, a next stage might be that you push a button, maybe this highlights or something like that, to make it more interactive. So that's a very simple example, something just ridiculously easy to do in Unity. You just attach a transparent texture map as a child of the hand. I talked previously a little bit about multiplayer. Unfortunately, I don't have a video of this and don't have a network set up to be able to show it. But multiplayer with tracked humans, in this case, all it is 2-track razor hydras and the orientation of the head from the Oculus Rift. Even with just those 3-track points, it's so compelling. It's almost like a surreal experience versus if you're playing, just a regular video game and the character is just kind of, moving around. Maybe he has natural movements, but this adds verbal communication. So here, you can see the idea is that me, the player, has got the enemy. He's got him in his sights. And as a result, the other player, just naturally puts up his hands. He doesn't have to think about what the mapping is. You get this very, this nonverbal, body language that you can't get otherwise. And also, we're not currently doing eye tracking. However, head tracking is very compelling. You kind of make that natural eye contact automatically without having to think. So that can be very compelling. And of course, when you move around, you may not physically be moving, but we have an animation so that when you push forward, the feet. And I'll show a little bit of that here in the demo coming up. Okay, now these different coordinate systems within virtual reality. I kind of showed here some examples of multiple coordinate systems. You can think of the first coordinate system as, might be a little hard to see. I don't know, can you guys see kind of a transparent circle, kind of some crosshairs there at all? It's more obvious in the Rift, but that's what you could call a head-centric coordinate system. So you could think of that as a helmet attached to your head. So wherever you're looking, then you always have that crosshairs in front of you. The idea here is that that's what you're aiming at. Now that has some advantages and disadvantages. One of the disadvantages is there's something close to your face. And so even though your eyes focus on a precise distance because it's a physical display, it's still your eyes kind of cross when you're focusing on something close versus far away. So that's a challenge. There's also a challenge if you walk into a virtual object. If I have a virtual helmet on and I go up to this wall, then what happens? The helmet is like as if it goes through the wall. So it's a little bit strange, but depending on the design of your game, you may or may not want to have something. Another coordinate system is your body coordinate system. So it's not shown here, but if you have an avatar, if you have a self-embodied avatar, you look down, you see your own body, right? And you see your legs. Or if you push forward, then your legs will move forward. I'll show a video of that shortly. But in that case, Oculus depends. Some people have the preference of when you move forward, then it should either move in the direction you're looking. So you can imagine, if my head is the same as the body, then on the controller or with my natural head motion, if I go like this, now I move, I push forward, suddenly forwards like this. It's as if my entire body, I can only do this. Myself, I prefer the method where the head coordinate system is different than the forward direction. So I can, I can do things like this. Or if if I do this and I say forward, now forward's going to be in this direction. So that's sort of a body-centric coordinate system. Another coordinate system I added here is a world coordinate system. And that is represented by these blue arrows. And this is a little bit hard to explain, but I'll show it briefly here in a few minutes. The idea of that is that these blue arrows match the real world. So you can think of it, augmented reality is sort of the inverse of this. Augmented reality is we might overlay these sort of basic visuals onto the real world. Here we're taking something, this represents the physical real world direction. So you could think about it where your keyboard is located. And no matter what I do in the world, that physical keyboard location is always going to be represented by those blue arrows. And I'll get a little bit more into that later, but that's what I call a world coordinate system. We also have a game coordinate system, which is represented by this W here for being west in the world, and for being north in the world. So if you look down in this case, I have a compass that kind of surrounds your body, and so depending how I move, I always know, it's real easy to get lost in a virtual environment map, because you're like virtually rotating, you don't have that sense of your location in the world quite as well, it's easy to get lost. And so this represents, it kind of keeps you engaged on the map, so that you know which direction's which. So if I always know this way's north, I'm not confused of, which direction was I heading again? You just look down and there it is. And that kind of, it's interesting because as you virtually rotate, how all these different coordinate systems show up on the display, it's kind of interesting. And it's something that you can explain, but you really got to kind of try it out to like really get the thing. Like you can get it intellectually, but you have to experience it to have everything come together without having to think about it too much. So those are some coordinate systems to think about as you're designing your applications. Okay, here I'll talk again about the those blue arrows. What are those blue arrows? And they're kind of weird. You don't see that in a normal game. Why did I add those? Well, it turns out that if you're in, say, a game with a cockpit, like a spaceship, then that spaceship cockpit acts as a world-stabilized cube. That is, if I turn my head, that spaceship's going to be that cockpit's going to be constantly out in front of me. Or if I'm flying the spaceship and I say turn left, the outside world's going to turn. You're going to be traveling through that world. Or even if you're just flying forward. But the cockpit is always going to be stable. It's not going to be flying forward. And that drastically reduces simulator sickness because now I don't have as much the sense of vection of me traveling forward in the world visually, even though my inner ear is saying that I'm stable in space. It's actually the inverse of motion sickness if you're in a car. If in a car, you're not paying attention to the outside surroundings, you're just trying to read a book or whatever, what the problem is that visually, your mind tells you, oh, I'm stable in space, because the book is stable relative to my head. However, my vestibular cues tells me that the car is accelerating, decelerating, turning, all those things. And that's a sensory cue conflict. So your mind gets confused, it says, what's going on here? Maybe I had some poison, or something bad happened. I need to eject that poison is one theory, sort of the biological genetic theory, that I need to eject that poison from my body, thus I get sick. Your mind gets confused. This is the inverse of that. Here, visually, if we push forward on the joystick, visually, our minds say, it looks like I'm moving forward, but it feels like I'm stable. My body is not accelerating or decelerating. So that's actually the inverse of typical motion sickness. But they're very related, and all the, we kind of know the basics as far as what's good, what's bad to do, but there's a lot of unknowns about simulator sickness, and that's very much a great research topic of what are specifics that get people sick. It's also very different across users than what causes sickness. What causes sickness for one person may not even affect other people. There's obvious things that we've discussed, such as visually moving forward versus holding still. But then some people get get sick when they strafe to left to right, or when they strafe left to right visually or virtually, but not physically. I don't have a problem with that. Or me backing up, I don't have a problem with that. But I get sick on other things. Some people do have a problem backing up. So it kind of is user dependent.
This example you have up, are you saying that you can add markers to scenes to reduce sickness?
Oh, yeah, so, thank you, good point. So to continue that conversation of the cockpit, this is something that doesn't have a cockpit, but this blue arrow kind of gives a reminder of if you kind of pay, and this is, I haven't done formal user studies on this, but I'd love to, continue this to see if there actually is an effect. What it feels like to me, and the few people that I've tested, that if you kind of focus on this kind of physical cue, this stable, it's a world stable reference cue. If you focus on this, then you're less likely to get sick. So as I touch that, it kind of decreases my sense of vection, that sense that I'm moving visually when I'm not moving physically.
And that's in the real world space, not the body space?
Yeah, exactly. And it's kind of something that's a little hard to explain, but when you try it out, you kind of get it. You rotate virtually, but physically that arrow is kind of, you can think of that of the keyboard or the desk or whatever sitting right there. And so it's kind of taking that cockpit form for a game that doesn't have a cockpit and simplifying it to something small. And I've also played with adding more than just one arrow, so there's multiple arrows. So it might be that in the peripheral vision, maybe that's more important than where the arrows need to go. And that is often the case that vection occurs for large fields of view. And that's one of the challenges with the Rift, is that it's such a wide field of view. I've had people try the Rift and they're like, I don't know what's wrong, like I don't get sick in other head-mounted displays. Well, in other head-mounted displays, when you have a field of view like this, you're not going to get sick. So it's because it's better, it becomes more difficult and more challenging. Okay, so here I have an example application. And then I will quickly get into showing the details of this application. See if the video plays. Okay, so this was something that, did any of you participate in the VR Jam, Oculus VR Jam contest? Okay, so Oculus put out this contest that they say you have little over 3 weeks, about 3.5 weeks, to create some games for the Oculus Rift. And then they gave out some prizes for that. There was about 300 entries. And so a massive quantity of, to be able to build up experiences built specifically for virtual reality. And so I participated in that contest. I created this game in about 3.5 weeks. And shortly after that, I met up with Jan, who I met at this conference last year. So you never know who you're going to run into or where they might go. But the reason why you should be doing real-world people networking here, not just computer networking. I ran into him, and shortly after the VR Jam, he asked to use my game that was going to be on ABC's Shark Tank. And so we integrated this game with the Virtual Omni, which is the omnidirectional treadmill. And so if you go to the gym, sometimes you'll have there's some games with a monitor in front of you, but you can only go one direction. This omnidirectional treadmill, you can go in any direction you want, which is perfect for VR. Because now if I look around and I want to run from someone, I just turn around and I can run. It's a pretty cool thing. So this is a short part of what was shown on Shark Tank back in December with the game integrated with the virtual. And let me see if I can turn that up. They do a really good job of kind of explaining virtual reality. Virtual reality, as you know, is something you got to experience versus just trying. Let's see if this.
Put on the virtual reality glasses.
Oh, cool. This is right up your alley.
The Omni enables you to
Oh, sorry. Let's try again.
put on the virtual reality glasses.
Oh, cool. This is right up your alley.
The Omni enables you to walk, run, jump, and crouch in 360 degrees and put your mind and your body into the video game to transport you into a different world.
Cool.
Wow.
Okay, Jan did a really good job of explaining and showing that versus sometimes you try to describe virtual reality to someone that hasn't experienced it before and it can be pretty difficult. Okay. So now what I'm going to do is talk a little bit, kind of show the highlights in Unity. All that was done in Unity, by the way, and a very simple port to the Virtuix Omni that has been improved since then. So that's kind of a very basic port. They had a Microsoft Connect watching you, and when they saw that you were moving forward, it faked it by moving the keys. It wasn't a great implementation, right? But now they have sensors so they can actually tell when you move properly and integrate it, more appropriately within Unity. Okay, so this is Unity, for those of you that have seen it for the first time, the development environment that we talked about this morning. And this is our scene graph for the game that we just showed. And I guess I don't want to take up too much time here, but basically, this is just how I configured the system. So we have the dynamic objects, which contains the Oculus VR player controller. And then I did things such as adding a helmet. So all I did was add a helmet as a child of the camera, and then added these crosshairs, which is just simply this texture. It's there's more specifics, but the concept is so simple to do within Unity. Versus having to do that all in code, it was pretty easy to attach. Obviously, there was code to do things here, but a lot of these basic concepts are really easy to do. There's also, of course, when you get shot, and you want to know you get shot, so I added some texture and such there, as well as some audio. This is like a collision detection, essentially, this capsule collider. So when the bad guys shoot at you, it does an intersection of a ray with your capsule collider to know if you got shot. We have the forward direction, which contains those arrows that I talked about, those real-world reference cues there's just some different arrows there. Let's see if I can bring that up. So there you see, there's my avatar and his big red bloody helmet for when he gets shot. But there's those blue real-world reference keywords. There's the avatar. For the head, you want to be careful. Basically, I got rid of the head, as you can see there, because if you use the avatar and the offsets, the position of the head is slightly off, then you start seeing like the back of the eyeballs or sides of the head. So you essentially want to remove the head, which we've got to be careful of when you have a network game, because if the player sees a different head than you not having it. It's a bit creepy to have an avatar. And then I have some lighting on there as well. But you can see there's just kind of a basic hierarchy there. You can see the entire scene. And there you go, there's the map. This map was very confusing before I had the compass in there, the north, south, east, and west. And of course the robots, these are the bad guys. And they have some basic AI. I just bought that AI asset off the Unity asset store, so I didn't have to write a complete AI engine myself. It was something like $50. The asset store is amazing. Let's see if I can find out where to zoom in on that. So there you go. There's a couple bad guys. Let's see what else. So the terrain, I went in and I painted the terrain and added some height and such. The basic map, again, I just bought off the asset store and I moved things around and such, but I didn't model, this was done in 3.5 weeks, right? Like, there's no chance, especially since I'm not an artist or not a modeler, that I could have, even just done the modeling by itself. So, I placed some trees and, some different assets that the modeling I simply purchased. Okay, so that's kind of the basic idea. I don't want to go into that in too much detail, but it's an example application, and let's see if we can actually run the thing. So I will run, and hopefully the Rift is plugged in. It looks like it is. Okay, so this is just the initialization screen to remind audio is very important. Not only that sense of presence that Lakulish is going to talk about later today about how to do better simulation within virtual reality, but here there's also instructions for the game. It's very confusing if you don't know what to do. And so you can, of course, look around, and then when you're ready to start, I have an Xbox controller that I forgot to plug in, but it also works with the mouse again. Not the best interface, but here you go. You can see, here it stabilizes. You can see you can look around. And you can see now, even though I'm looking this way, as I push the forward key on the keyboard, forward is not the way I'm looking, it's in the direction of my body, which if I look down, be like so. Let me try to rotate my body. It's a little hard to see because this model has a large torso. If I walk forward, you can kind of see my feet. So there we go. So even though the hands aren't tracked in this case, like with the Razer Hydra controllers, the reason why is the VR Jam, they wanted it to work with any system. I really wanted to use the Razer Hydra, but not in this case. You can see.
You may want to avoid wide open spaces.
It's a little hard without actually being in the Rift, so let me go ahead and put that in. Okay, so now let me get my sense of direction. Now you can see those blue arrows, and it will be hard for you to see them, but as I go forward, look down at my feet. I'm get out of here.
Things outside.
Okay, so as I, no matter which, see how I'm moving? But these arrows are also always physically in front of me. So what it appears like me, you guys probably can't tell there, but here in front of me is the direction of the arrows. Even if I turn, the arrows still are physically in front of me where my keyboard is located. If I do like that, now the arrows are to my right, they're still physically in the floor. And of course, here, let's go try to find the, this is why a keyboard interface is not the right interface for
15
VR.
seconds until
It's hard to
detonation.
find.
10,
Now this guy,
9, 8, 7, 6, 5, 4.
and I made it a very short timing. You're supposed to defuse the bomb, which I did not do well. I did not defuse it in time. You could see there was a bomb that exploded there in the distance. Game over. Okay, let's see if I have anything else here.
You're relying on the magnetic calibration to keep your world stable markers in front of you.
Yeah, this is, it's not perfect, the magnetic correction to keep it from drifting. And so there's different options to push buttons. I didn't show it there, but like on the Xbox controller, you can recenter your view. So if it drifts too much, you can say, hold on, let's make sure those blue arrows are actually where I expect them. Otherwise, suddenly you're facing like this, which used to be previously. And other options, for example, the helmet. We can turn off the helmet, or we can turn off the blue arrows. Because some people, while turning off the blue arrows is great because you can compare what it looks like without the blue arrows, and it doesn't feel different.
With the camera track F2, we expect that not to be an issue with the drift.
Yeah, exactly. Assuming they're getting some orientation, absolute orientation information. Okay, and this was an example I wanted to show of how you blend animations for the feet moving together. That is done. Oh, that's under the forward direction. See, is always the self-embodied avatar because that's the torso. And so here, you can blend animations together. For example, the feet. If you look down, if you straight, the feet go like that. But if you walk forward, then the feet move differently. But if you walk this way, it will blend different things, blend the different animations together. And so it's hard to see here because of the low resolution. But this is basically just a state machine. And actually, Arno later today is going to talk about more realistic humans with the virtual human toolkit that does more advanced things, more options, whether it's speech recognition, whether it's being able to control the state of avatars better. So I'm looking forward to that talk, so definitely come back later today. Akilish will be talking about, he'll be talking about quality simulated audio, so you can actually do it properly instead of faking. And who we have now is Sebastian, who's going to be talking about how to generalize input and output for virtual reality, so with Unity. And so I showed something that's very specific to the Rift and the Razer Hydra controllers, but his work, his tools, his asset store that's available, his asset that is available in the asset store that he'll be talking about is great because you could use the same application within a cave, or if you have different types of tracking, you could use that. It's really generalized to work with all sorts of different hardware. Okay, with that, that's my part of the talk. And now please help me welcome Sebastian up to the front of the stage.